Are there any questions? No? We're just going to continue with chapter 8. Next week is the test. Well, this is going to include the rest of 7, 8, 9, and maybe part of 10. It's likely not all of 10 will be covered there. 9's a pretty short chapter. And so we're almost done with chapter 8. Chapter 8, we're talking about the Bohr model here. And this is the first quantum theory for the atom. We should just take a look at some of the features of this particular model. Yeah, what Bohr stated was that the electrons orbit around the nucleus, and that there were certain orbits that were allowed, certain orbits that are forbidden. And so all this gray zone is forbidden, just the black lines are allowed. And so the first allowed orbit is this n equals 1 orbit. The n equals 1 orbit is going to have a radius that's going to look like this. It's going to just be n squared times a naught, where a naught is 53 picometers. And so when we have n equals 1, then the radius is 53 picometers. And so when the electron's in this first orbit, it can orbit at 53 picometers, but can it orbit at 52 picometers? Is that possible? Or 54 picometers? No, those orbits aren't allowed. The next allowed orbit is when n equals 2. When n equals 2, then r is going to be 2 squared a naught, so 4a naught. So 4 times 53 is going to be what? 112 picometers? 2 times 53, 212 picometers. And so this next orbit's at 4a naught. That's what they're showing here. And that's allowed. And so why aren't orbits, shorter or longer, just by a little bit, 53, possible? Why do we have to jump all the way to 212? And so what did Bohr say? Well, what this gets to is what exactly does science tell us? Does science tell us why? Well, a lot of scientists will just say, no, science just describes nature. And this is a pretty good description because it just can't. And so why who knows why? But, this is what's observed in nature. And so these are something called like the postulates of quantum mechanics. Have you heard of a postulate? Postulate's just taken without proof, And the proof is in the observation. Well, this is what's observed. Likewise, we can get the energies from these, just using some physics. Using some physics, we see that the energy depends on n. N is sometimes it's called the energy level. So this is the first energy level, that's the second energy level. And so the energies are just given by this equation, minus r sub h over n squared. And so this orbit here has an energy of minus 2.178 times, or 2.179. 2.179 times 10 to the minus 18 joules. It's energy. All right, the second orbit, we can determine the energy for this. That would just be E2. The energy for that is going to be minus r sub h over 2 squared, which is 4, so just 1/4 that. Dot, dot, dot. So visually, this is the picture we see. Now, how far do these energy levels go, or these orbits go? Well, they go all the way to n equals infinity. And so if we go all the way to n equals infinity, then what's the radius of that orbit? The radius of that orbit is going to be infinity squared times a naught. In other words, the electron is going to be at an infinite distance from the nucleus. Now, what does that mean? How can you get an electron infinitely far? Well, basically, it doesn't have to be an infinite distance. Basically, what we need is the electron's no longer under the influence of that proton. And so what we call this is, we call this an ionized electron. The electron's been knocked off the atom. Ionized electron. The energy for this is this. It would go E sub infinity. E sub infinity is just going to be minus r sub h over infinity squared, which is going to approach 0. And so when we map this out in an energy level diagram. So let's go ahead and take a look. And so the orbits just, actually, something interesting happens with orbits, although it doesn't really look like it. You know, it looks like orbits progressively get bigger and bigger, like an onion shell. But the orbits get progressively larger. And so this is at 4, this is going to be at 9 times this is at 16 times the distance. Although this is not really drawn to scale. All right, here's the energy, and so we'll take a look at what the energy levels look like. Here it is. This is all the energies from 0, not 0, actually, what's the lowest energy it can have? The lowest energy, normally we think of the lowest energy as 0, you know, that's the lowest energy. But this energy is a little bit weird because this energy is actually negative. How can something have negative energy? You know, let's say if something has negative 2 kilojoules worth of kinetic energy, what does that mean? Normally what we associate the negative sign is we associate that with an exchange of energy. And so if something has a negative energy, we usually think, well, it lost that amount of energy, right? It lost. But in this case, when the electron's in the first orbit, that is its energy. The energy is minus 2.179 times 10 to the minus 18 joules. And so does that mean the electron is orbiting backwards? You know, and if it was orbiting forwards, it'd be positive. You know, what does a negative in this case mean? Because that's just the energy of the electron. Well, what it means is that, you know, oops, actually you can't see it down here. The lowest energy the electron can have is n equals 1, which corresponds to the first orbit, which is negative 2.179 times 10 to the minus 18 joules. So what is the negative energy there? Electron's orbiting. And so what we need to know is we need to know how the 0 is defined. What is the 0 energy? We'll scroll up here and we see. Here we have 0. You see E infinity is 0. And so the 0 is defined as this. This is not the total internal energy. If we're looking at the total internal energy takes into account the kinetic energy and the potential energy. When you have ionized an electron, you still have the proton, you still have the electron, right? And the electron's always moving. And so that means that means that this is an arbitrary 0. Right? An arbitrary 0. The arbitrary 0 is just, okay, the highest energy, when we're looking at the energy of the electron, you know, it's going to be n equals infinity. N equals infinity, the energy at infinity is equal to 0. And so we're just defining it relative to this. When the electron's infinitely far away from the nucleus, then that's 0 energy. As the electron gets closer and closer, you know, the energy goes down as it becomes stabilized. And so it's going to cost you energy to separate it. One way we can kind of visualize that is way out here. Let's say this is the distance, or the r. Way out here, there's an electron infinitely far away. Well, that's our 0 in energy. As we bring the electron closer to the nucleus, there's going to be an electrical attraction. Eventually, the energy drops down. And so this is called an energy well. And so what we're looking at here is this energy well. You know, as the as it becomes more and more stable as the electron gets closer to the nucleus. Well, one question comes up is, what would the lowest energy be? Well, the lowest energy would be, if it wasn't 53 picometers from the nucleus, we just bring the electron all the way to the nucleus. And so we let the electron go to the nucleus as that electrical attraction. That's going to stabilize things even more. And so this potential well should drop all the way until the electron hits the nucleus. But will the electron hit the nucleus? No, the electron will never hit the nucleus. The electron won't hit the nucleus because it can't orbit any closer than 53 picometers. Well, why can't it orbit any closer than 53 picometers? Why? Why can't the electron just shoot straight to the nucleus? There's electrical attraction. Is there an invisible wall or some kind of force field or barrier that prevents it? What is there? Well, what's there is empty space. There's no invisible wall. Or maybe there is, And so what's preventing the electron from going to the nucleus? Now the proton is pulling it in like a tractor beam, in the sci-fi movies, if there's a positive proton in the center here, the electron's being pulled in, like this, by the electrical forces. And so the proton's trying to pull in the electron, but it hits 53 and it stops there, and it can't get any closer. Why? Why is that? Well, to be a naturally curious person, you're going to ask why. But it's tough because what's the answer to that? The answer is it just can't. It's not observed in nature, and that's it. That's why it can't do it. Why can't it do it? I don't know, but it doesn't do it. Right? And so this is it. This is where it goes, and that's what there is to it. Well, you know what? Is when you look at the energies, what happens is E2's here, E3's here, and they progressively converge here. Because how many lines do I have to write between 1 and infinity? How many lines do I have to write? When I get to E 1 billion, it's here, and then E 1 billion and 1, E 1 billion and 2, eventually trillions, and if I had to write every line here, I'd never be able to do it because there's going to be, how many? An infinite number of lines, and pretty soon they're going to kind of converge. So they start off as spreading this kind of big, you can see it here. From 1 to 2 is a big jump, 2 to 3 is a big jump, 3 to 4, 4 to 5, 5 to 6 is going to be a smaller, 6 to 7 even smaller, and then eventually we have to compress between 5 and infinity, like an infinite number of lines there. And so it's going to get quite messy. That's what happens with the energies. The energies converge here at 0. 0 is an arbitrary 0, just based on separating the electron from the nucleus. What happens to the radii? The radii diverge. If you look at the radius, it just keeps growing bigger and bigger. The next one's 16. The next one after that's 25, 36, etc. Radii get huge. So this atom grows exponentially, or just grows bigger, and the energy levels kind of compress there. Okay. When we're thinking about it, think about this energy. Minus 2.179 times 10 to the minus 18 joules. That's how much energy is stabilized by bringing the electron to the nucleus and putting the electron as close as it can get to the nucleus. This is as close. And so, having the electron separated is higher potential energy. As we bring the electron closer, it drops down in potential energy. And so this is the energy that's released in bringing the electron close to the nucleus. Well, to take the electron away from the nucleus, we have to add energy to this. And that energy is given a name. So if we take an electron from the lowest energy state and bring it to the highest energy state, this process is called ionization. And the energy that's involved is called the ionization energy. Let's calculate the ionization energy for the hydrogen atom. The ionization energy is just going to be equal to this. The energy is equal to E final, this is delta E, E final minus E initial. And so the final energy is going to be 0 joules. The initial energy is 2.179 times 10 to the minus 18 negative. So this is a minus 2.179 times 10 to the negative 18 joules. And so the ionization energy is 2.179 times 10 to the minus 18 joules. And so that's the amount of energy that's required to strip an electron off a hydrogen atom. Is that much energy? 10 to the minus 18 joules. Now, if you're thinking about it, could you heat up a cup of coffee with that? 10 to the minus 18 joules? You had a cup of coffee and you added 10 to the minus 18 joules. Are you going to register any temperature change? Oh, no. That amount of joules will do nothing to a cup of coffee. And so what we have to do is we have to be careful when we're dealing with energy, because there's two energies that we typically deal with. One is like the total energy. The other is the energy for an atom or for a photon. You know, when we're dealing with things like in chapter 7, well, we're not just dealing with a single atom, we're dealing with mole quantities. 250, that's over 10 moles, 12 moles of water. 12 moles of water, obviously this is not going to do anything. But to a hydrogen atom, this is to a single atom. And so when we're dealing with energy, you have to be careful, with energies. We need to put this energy into perspective. And so that energy that is required here, energy is 2.179 times 10 to the minus 18 joules. This is really joules per single atom. But typically we deal with moles of atoms. And so in terms of moles of atoms, we take this number and multiply it by Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. And when we do that, what do we get? So let's take a look. And so I'm going to take the 2.179 times 6.022. This is not a scientific calculator. 13.12. 13.121 times 10. 18 minus 18, that's going to be times 10 to the 5th joules per mole. So this is going to be 1,312.1 kilojoules per mole. And so if we look at a mole of hydrogens versus a single hydrogen atom, then we're looking at thousands of kilojoules worth of energy. And so it depends on who you're talking to. If you're talking to somebody and they're doing a calorimetry experiment, they might be using joules, hundreds of joules, or thousands of joules. But when you're dealing with something at the atomic level, we're dealing with minuscule quantities. But these minuscule quantities are actually quite big because 10 to the minus 18 joules is comparable to 1,000 kilojoules per mole. And so this leaves the opportunity to get mixed up in energy calculations. So let's take a look at the problem here. The energies, we have to be able to flip, from one perspective to the other perspective. And so let's take a look at chapter 10 here, bond energies. All right, now let's not deal with ionizing a hydrogen atom. We're going to look at breaking a hydrogen-hydrogen bond in an H2 molecule. In order to break a hydrogen-hydrogen bond in an H2 molecule, how much energy do we need? Well, we look at 435.93 kilojoules. Right? And so let's go ahead and do a calculation here. And the calculation is this is an example of energy. What wavelength of light is required to break a HH bond? And the energy for the HH bond is 435.93 kilojoules. And so if I shine energetic enough light on this, it can break it. It's a photo dissociation. Light can be used to break bonds. This is why some chemicals are stored in light-proof containers, like iodine. You know, iodine's bond is really easy to break with light. Hydrogen peroxide. You wouldn't want to store hydrogen peroxide in a clear container. Light will decompose that. Well, anyway, we go here. If we look back at our energy equations, energy is equal to H nu, which is equal to Hc over lambda. And so we want to solve for lambda here. And so lambda is going to equal Hc over the energy. We have to be careful about energy because, you know, if energy comes out negative, right? It means it's exothermic. If energy comes out positive, it's endothermic. But is energy itself negative or? No, energy itself is not negative, you know. So that's exothermic. And so if we end up with a negative because it's exothermic, it's emitting light rather than absorbing it, we want to change the sign. You know? So oftentimes we'll put an absolute value there. Otherwise you'll get a negative wavelength. And what does a negative wavelength mean? You know, -1 centimeter wavelength. So it doesn't have a physical meaning. And so, with that. And then we'll just plug it in. So lambda is equal to H. H is 6.626 times 10 to the minus 34 joules times seconds. This is called Planck's constant. And it's given the symbol H. Joules times seconds, you know, joule per second is called a watt. A joules times a second is called a unit of action. Whatever that means. Okay, that times C is 2.998 times 10 to the 8 meters per second, divided by E, the energy, 435.93 kilojoules. We need to change kilojoules to joules. This will be 1,000 joules per kilojoule. And that should give us the energy, the wavelength. And so let's go ahead and do that here. If somebody has their calculator, could do it faster. No. But I'll get 6.626 times 2.998 divided by 435.93 divided by 1,000. 4.5568. 4.5568 times 10 to the minus 5 from the calculator, and then I gotta handle this. 10 to the minus 34, 10 to the 8, which would give us 1 times 10 to the minus 26. So this gives us 4.556, we're allowed 4 sig figs, so substitute the 8, times 10 to the minus 31 meters. I had to do that extra step because this calculator doesn't let me do scientific notation. All right, and so when we're done, right? Does that look okay? Actually, no. This doesn't. Why doesn't it look okay? Well, I made a huge error, but maybe you'll see it, maybe you don't. One, when we deal with a lot with big numbers and small numbers, it's hard to understand. This is just like any other. Avogadro is a tiny number. This is a tiny number. This 10 to the minus 18 joules. 10 to the minus 18 joules is, if you try to heat up a cup of coffee and somebody said, I'll give you 10 to the minus 18 joules, right? It's totally worthless, right? It's totally worthless. And so we deal with these numbers, and so some of the numbers we know. Like if somebody said, well, I'm going to give you 10 to the minus 18 joules, it won't do anything. And there's no use in pursuing that any further, right? But somebody who doesn't know the numbers, they might think, oh, 10 to the minus 18 joules, that's going to heat up a cup of coffee nicely, right? Maybe. But if you give that amount of energy to a hydrogen atom, that will do something significant. And so let's go back, and I asked you to memorize some wavelengths. What wavelengths did I ask you to memorize? Visible light, right? Visible varies from what to what? Well, I asked you, visible varies from 390 to 760 nanometers. And then, well, if you have a wavelength like this, 10 to the minus 31 meters, what kind of light is that? And so the thing is, did you know that's a ridiculous wavelength? Kind of like 10 to the minus 18 joules would be to a cup of coffee. Did some alarm bell? No, probably not, right? Because you just don't know. And so, a lot of people say, oh, don't memorize because you can always Google it, but you don't have the opportunity to Google everything. Wait, let me Google that, and sometimes you aren't gonna, what if the internet's down? Then you're gonna be out of luck. And then, here, so what we should know is this, and so you should get some clue. Radio waves are like, is that 10,000 meters? 10 kilometer wavelength? Radio waves. And so waves vary from about 10 kilometers of radio all the way up to gamma, which are going to be at 10 to the minus 16 meters. Gamma's at 10 to the minus 16. And so we go from 0, 10 to the 0 would be in the radios, a meter, to 10 to the minus 16, and we pass by all these, And so within a span of about 10 to the 15 meters, we're there, right? Over the entire spectrum, 10 to the 16, 10 to the 15 meters. That kind of range. Well, 10 to the minus 31, where's that? Well, that's like 15 more orders of magnitude out there. 15 more orders of magnitude out that way. Well, we just passed by 15 orders of magnitude here, starting at radio to gamma. Now we got to go another 15. And so are there another 6 or 7 types of light you have to memorize? Or does gamma ray take care of it? That would be a gamma ray? No, there's something seriously wrong, right? Something seriously wrong because we're going from 10,000 to 10 to the minus 16 meters here. And so this wavelength doesn't make any sense. 10 to the minus 31 meters just doesn't make any sense. And so, and the reason is this. Do you guys recall quantum stoichiometry? Quantum stoichiometry. Quantum stoichiometry says what? From Thursdays. Quantum stoichiometry. No, not that. Not that light is quantized. something a little different. Quantum stoichiometry is like this. One photon per one electron. And so what this means is this. I'm trying to use one photon of wavelength 10 to the minus 31 meters. This is the energy of the photon that's required. And so what I'm going to do is I'm going to throw, let's say, one photon at an Avogadro's numbers worth of hydrogen atoms and ionize them all. And so this would be like the end of the world photon, right? Because this photon would pack so much energy, it could ionize an entire mole of hydrogen. You aren't going to see that kind of energy because that kind of energy to a hydrogen atom or an atom would obliterate the atom, right? And so this amount of energy is enormous for an atom. And so in other words, what I'm trying to do is this. It's like I'm trying to throw one baseball and hit everybody in the baseball stadium. Is that going to be possible? Well, even if I throw it super hard, you know? No, it's not possible. And so the problem is this. This is one photon, you know, for a whole mole of electrons. Not a whole mole of bonds, but for a whole mole of H2 molecules. And so that's why it would be like the end of the world, because that would have to have so much energy it could ionize, not ionize, but break like an entire mole's worth of bonds. And so the major mistake I made was not mixing up the energies. You know, oftentimes we leave off the mole, you know, especially in chemical reactions. We don't write that there. You know, this 435.93 is for the reaction as written. And so oftentimes when we'll see this is, you know, we start off with an H2 and we go to two H's. Delta H for this is going to be 435.93 kilojoules, right? That's normally how we write it. But we have to be careful because when we're dealing with photons, we're not dealing with mole quantities. You know, this as written is per mole of this, per 2 moles of hydrogen atoms that are generated. What we're dealing with when we're dealing with photons are individual atoms or individual electrons. And so when we do that, then, or individual molecules. And so we have to redo the energy. And so this 435.93 kilojoules per mole of hydrogens. But what we want is we want the energy per H2 molecule. But need the energy, you know, per H2 molecule. And so what that means is we have to do an extra step here. And the extra step is 435.93 kilojoules per mole of hydrogens translates to, well, in a mole of hydrogens, there are 6.022 times 10 to the 23rd H2 molecules. And so that's going to equal what? So let's get the calculator here. It's 435.93 divided by 6.022. 72.389. This is going to be kilojoules per H2 molecule. Oops, times 10 to the minus 23. other words, let's rewrite this. Actually, maybe I should write in joules. It doesn't matter. 72.389 times 10 to the minus 23 kilojoules per mole. And so we went from a lot of kilojoules here to 10 to the minus 23, 10 to the minus 24, 10 to the minus 22. And so the amount per individual molecule is quite small. Actually, I got to convert that to joules. And so let's redo the calculation here. And so lambda is going to be hc over this now. It's going to be 72.389 times 10 to the minus 23 kilojoules. And then convert that to joules, 1,000 joules per kilojoule. And so H 6.626 times 10 to the minus 34 times C 2.998 times 10 to the positive 8 divided by 72.389. Screw that. 72.389. 0.2744. One. This is 10 to the minus 34, 10 to the 8 gives 10 to the minus 25, 10 to the minus 25. Oh, actually, what is this? 10 to the minus 34, 10 to the positive 8, 10 to the minus 25. Bring that up. Did I? Yeah. This would be 10 to the third, 10 to the minus 20. It would be 20, 10 to the minus 5. This would be times 10 to the minus 5 meters. Is that right? I should bring a scientific calculator. I'm going to change this. I'm going to change it to 10 to the minus 9 meters. I think I made a mistake. 10 to the minus 6. 10 to the minus 6. Let's see, 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. Did somebody punch it out?
Yeah, it comes up to 274 nanometers, so yeah, 2.7.
All right. So we do 274.4 times 10 to the minus 9 meters. 10 to the minus 9 is a nano. And so this comes out to 274.4 nanometers. All right, does that seem reasonable? Well, where is 274 nanometers at? You should know without looking at this chart. If you look at the chart, where is it at? Ultraviolet. And so that makes sense because what does ultraviolet light do? Ultraviolet light breaks bonds. And so we shine UV light on it to break bonds. Okay. And so we have to be careful with the energy. All right, let's go back to the Bohr model. And so Bohr, this is pretty successful because Bohr's saying, light emission or light absorption. Absorption, we're just promoting electrons to higher orbits. Emission, these excited atoms are dropping back down in energy and releasing light, emitting light. It was pretty successful for the hydrogen atom because, Bohr here, what was observed are these lines, the red, the green, the blue, and the violet's not shown. The violet goes from E6 down to E2. But, there are higher energy lines that aren't visible to the eye. For example, there's a whole series of lines in the UV. These are called the Lyman series, after Lyman who observed it. And so from this model, you know, we could see that we could also generate lines in the UV and lines in the infrared. Because the lines in the infrared are going to be from, for example, 4 to 3. You know, that's smaller than red, the gap there. So this would be infrared, infrared, infrared. So there are a whole series of lines in infrared. Those are named after somebody as well. I forgot who, Redbird, I think. But it seems pretty successful. So the model seems pretty easy to understand, I think, if you just take those postulates. Now, the problem is Bohr, you know, theory gives us a pretty good fundamental picture of things. You know, electrons orbit. And it seems to have predicted this. But what should a theory do? A theory should give us a fundamental picture and predict. And the problem with the Bohr model is it couldn't predict the spectrum of any other atom. Right? The only thing it could predict are other one-electron species, but one-electron species aren't that common. And so, unfortunately, if the theory doesn't agree with the experimental facts, then there's something wrong with the theory. And so, well, what do you do? Well, the Bohr theory was no longer valid, so wasted already a lot of time talking about the Bohr model, but Bohr model didn't work. And so what should we do? Well, we got to get rid of that theory and start over again. And so what do you do? We're going to use the scientific method. So what do you do in the scientific method? Do you do a hypothesis? So you can do a hypothesis and test your hypothesis? What would your hypothesis be? Were there two competing hypotheses? So for example, there was a Bohr model versus what model? Do you remember during Rutherford, there was the plum pudding model versus the nuclear atom model? So if the nuclear atom didn't work, there was a plum pudding to fall back on. But what about this? Is there another alternate model? And so all you could do is you go on and hopefully take more observations and see. Well, what kinds of observations? Well, there were two developments that happened. You know, there's nothing wrong with these lines. You know, the theory, these are experimental fact. The spectrum is experimental fact. Yeah. This is obviously not hydrogen because there are a lot of lines here. This is emission spectrum. These are the colors of light that are emitted when the electron goes from a higher level to a lower level. This is absorption. When you shine the rainbow colors and see what colors of light are absorbed, they're the electrons going from a lower level to a higher level. That's fact. Those are fact. And so whatever theory we have, you know, it has to agree with fact. Well, basically two things led up to a revision of the Bohr model. And the new model is called quantum mechanics. This is our modern day theory of the electron and the atom. And so two ideas led to new quantum mechanics, or two developments. One is this person here, de Broglie. De Broglie came up with this whole idea of wave-particle duality of matter. There's already wave-particle duality for light. You know, a particle of light is called a photon of light. Although it's not a particle in the sense that it has mass. It doesn't have mass. In a lot of ways, it behaves like a particle of light. Well, what de Broglie says is that all matter displays wave-like properties. And so here's the development of that idea. But basically, we end up with this equation, this de Broglie equation. This de Broglie equation says that the wavelength of the matter, and so wavelength of matter, this is not light. Right? The wavelength of light is equal to c over nu, or hc over energy. Well, the wavelength of matter here, this is going to equal h, again, which is Planck's constant, divided by p. P is momentum, which is mass times velocity, or the energy. And so this is going to be h over mass times velocity. Planck. And so if something's very massive, then the wavelength is going to be extremely small. If something's moving very fast, the wavelength is going to be small. As things become smaller, the wavelengths get bigger. The size of the wavelength is important in its interaction with matter. So, for example, if the size of the wavelength is comparable to the object itself, let's say we have an ocean buoy, and there's ocean waves here. As the ocean waves pass by the buoy is going to go up or down, right, depending on how it goes. And so when the wavelength is comparable to the size of the object, we have something like this. But, if the wavelength is short compared to the object, it's not going to affect it as much. So if there's a big ocean tanker here, it's not going to be oscillating with these waves like a buoy would be. The ocean tanker just go right through there. But the way we're going to look at it is in a little different context. Is an electron, if it has a wavelength, then we have to account for that, or we have to factor that in. Now, how do we factor in the wavelength of an electron? Let me just show you the figures here. We factor it in like this. Now, let's say there's an electron that's confined in a box. What was another figure for this? Here. Let's say we have an electron confined in a box. What's going to happen, because of the wave property of the electron, we're going to have constructive interference and destructive interference. And so here, this would be termed an allowed energy. And this allowed energy is when we have a half a wavelength here. But we can't have anything, a little shorter than half a wavelength or a little longer than half a wavelength. The next allowed energy would be when we have an electron here with two half wavelengths here. Now, the analogy would be like a musical instrument string. And so if you have a string, and you pluck the string, you're going to be able to fit a half a wavelength in there. If you pluck it harder, you just don't get a little bit more than half a wavelength, just a little bit higher in energy. Actually, that's going to be forbidden. The next allowed energy is going to be when you get two half wavelengths in there, be an overtone. And then you pluck it even harder, the next one will be much higher in energy, which would be 3 half wavelengths. And so we already see that standing waves in a string are quantized. They're quantized based on half wavelengths. So this is n equals 1. This would be n equals 2, 2 half wavelengths, 1 half wavelength. This would be n equals 3, where we get 3 half wavelengths. And so we see the quantization of energy in standing waves on a string. Well, if an electron has wave properties, then it's going to behave in exactly the same way, in the sense that the electron, if it's confined in a box like this, we can only fit half wavelengths of energy in here. And that's it. Okay, this is going to have an impact depending on the size. For example, if the wavelength is comparable to the size of the box, then this quantization is really apparent. And the size of the box is the atom. We're confined to a box, the box we call the atom. But if the box is big, then, you know, then the wavelength isn't such a big factor. And so it depends on the wavelength versus the size. And so, you know, the size of the box is very small. You get something like this, okay? And then the next allowed energy, and then the next allowed energy, etc. And so we get energy levels like this with spacings. N equals 1 here, N equals 2, N equals 3. And that's a pretty big jump, you know, in terms of energy. You have to hit the string a lot harder to get this energy, right? And so this is a small box, like an atom. If we have a very big box, this is a big box. A big box would be like a metal filament, you know, for example, or metal bar, like an iron bar. You know, if I had an iron bar like the spatula, oh, brand new spatula. And the electron is in this bar. This is a pretty big box compared to the size of an atom, because electrons in metals are pretty free, right, to move about. And so that electron, this is like having a gigantic aquarium, right? This is like having a tiny aquarium and a big fish. But if you have a gigantic aquarium, then no problem, because it can swim at any speed it wants, right? Whereas something that's confined like this can't swim at any speed it wants. And the reason it can swim at any speed it wants is because, let's say, you know, if the wavelength is small compared to the box, then we get a lot of half wavelengths in here. Let's say we could fit 1 million half wavelengths in there, or 1 billion. Okay, if n equals, let's say there's 1 billion half wavelengths in there. What's the next allowed? Energy. Well, the next higher one is you'd have to pluck it a little harder if it's a string, right? But how much harder do you have to pluck it? You have to pluck it really hard to get this overtone here, or just a little bit? Well, it turns out just a little bit, because the next allowed energy isn't a big jump here. The next allowed energy is n equals 1 billion and 1 half wavelengths. And so what's the difference in energy between having 1 billion half wavelengths and 1 billion and 1 half wavelengths? Nothing. In fact, the next allowed energy is just right on top of this. Barely any difference. And so on. So the next one after that would be 1 billion and 2 half wavelengths, 1 billion and 3. And the energies are so tightly spaced. The energies are so tightly spaced that the iron bar, you know, when we heated up the iron bar, did you see lines or did you see a broad band? Well, you heated up to white light. Were there any forbidden, or was it continuous? It was continuous. And so essentially what we have here is we have tightly spaced energies. These are so tightly spaced that it's pretty much continuous. So it can absorb infrared and emit infrared. It can absorb red light and emit orange, yellow, and anything in between, because we got so many energy levels here that, you can promote it.
When you confine it to a small box, like that one right there,
Yeah.
it's for it to be n equals 1 billion. Does that kind of mean that it would go into like a particle? Because it's just like...
Yeah, once you get to very high energies, this is what's going to happen with this. what's going to happen is either you have a big box like this, or the wavelength becomes small compared to the size of the atom. And so if the atom's like this, we have this, and then etc. But when we start getting up here, when we fit 1 billion half wavelengths in here, what's the next allowed one? 1,000,000,001. And so the exact same thing happens in an atom when you get to very high or very short wavelengths, very high energies. And so for the hydrogen atom, it looks like this. When we look at the spacing in the energy levels, n equals 1 starts off like this, and then there's a big jump to 2, 3, 4, but we have to put an infinite number of lines all the way to n equals infinity. And so by the time we get up here, the spacings are so tight, it's pretty much continuous. Here. And so here we're going to see prominent, forbidden, and allowed, but once we're up here and we try to promote, then pretty much any energy is absorbed. And so if we have a high energy electron here and just kick it up a notch, no problem. It can pretty much absorb any energy it wants. And so it converges and compresses, and the energy levels become more continuous. And so we call this a band of energy levels. And we end up with a band here, It's pretty much continuous throughout here. And so this is why, like the iron bar, actually, why are the lights off? This is why, like, the iron bar is black body emitter. White light bulbs, black body emitter. But if you were to take an iron atom from this, this would be like an iron bar. But if you take a single atom of iron, then you're going to have forbidden regions and allowed regions. And so when we look at the spectrum for the iron bar, the spectrum of the iron bar is going to be black body light. Big band of allowed energies. Right? When we look at the spectrum of an iron atom, there are gaps, forbidden and allowed regions, like this. In fact, maybe I'll just show you. Let's see if I have the spectrum. So this bottom one's iron here. Do you see for an iron atom, there are regions of forbidden energies. Whereas when we looked at the iron bar was continuous, like this. And so that just depends on the size of the box. You got a big box, this quantization isn't going to be such a big issue. And so this is why a lot of people, when they think about quantum, a lot of people say, quantum deals with very, very small things. Yeah, and we notice that when things become quite small, then the wavelength properties become more significant. When things are quite large, are the wavelength properties very significant? No. And this is why they didn't notice or compensate for this, because if you throw a baseball compared to an electron is extremely massive. And so if an electron has a wavelength like this, a baseball's wavelength is way smaller than that. And so if you throw a baseball, and let's call it a standing wave, then pretty much any speed for the baseball is allowed. There's no forbidden speed because it's all, if the wavelength is so tiny that fitting another half wavelength in there is no big deal. So baseball speed is continuous. Whereas an electron, it depends on how big the box is. Even if this box is quite small, well, you can't make the box very small because the baseball itself is massive, and the wavelength compared to the baseball is extremely small. And so it's impossible to make a small box for a baseball. But whereas electron, the wavelength is quite big. And so the matter now, in terms of an atom is not a 2D box. An atom is a 3D box. And so let's try to visualize what's happening with an atom here. With an atom, we can see, for example, this would be an allowed energy here. The atom, this circle just represents the atom here. The curved path is the path of the electron. And so we fit in 1, 2, 3, 4, 5 half wavelengths. That's allowed. But this is not allowed, you know, because here we're fitting like 4 1/4 wavelengths in here or something like that. And when we don't get enough half wavelengths, what happens is it becomes offset. As it becomes offset, what we have to deal with are properties of waves. Two properties of waves would be destructive interference and constructive interference. Destructive interference happens when a peak and a valley coincide. And so you have positive amplitude and negative amplitude, they cancel each other out. And so the wave cancels itself out, and this is called the forbidden energy for this electron. And so this is how we visualize a standing wave in an atom. But it's not exactly like that because the waves look different three-dimensionally. Okay, the other development that came about is wave-particle duality, de Broglie. The other thing that came about is the Heisenberg uncertainty principle. So let's talk about that. And so, as far as atoms go, we could draw this out. You know, when the wavelength is about the size of the atom, then it's significant because here we get 4, and the next one will be 5 humps, right? But we can't have 4.5 humps. So there's going to be a significant change in the energy. But let's say if the wavelength were small, you know, compared to the atom, then let's say I had 1 million half wavelengths here. What's the next allowed one? You know, the next allowed one would be 1,000,001, which is barely any energy higher. And so this would be big. This is, you know, this depends on the magnet, the size of the wave. Big box or short wavelength. Okay, then comes the Heisenberg uncertainty principle. Heisenberg uncertainty principle. And so is this what the electron looks like in an atom? Like this? No. This is not what an electron looks like in an atom. You know, this is just kind of trying to conceptualize it. What does an electron look like in an atom? Well, you know, what is its path? How does it move? Where is it at? Those types of questions are very difficult to answer. Because the Heisenberg uncertainty principle says something about the uncertainty in position. Times the uncertainty in momentum or energy. Uncertainty in energy. The uncertainty in position and uncertainty in energy has to be greater than or equal to h over 4 pi. Over 4 pi. There's a fundamental limit to how precisely we can determine these quantities, according to the Heisenberg uncertainty principle. And what that means is if we pinpoint the position, so let's say we determine where the electron is in the atom, and we pinpoint the position of the electron. The proton, here's the electron, so it's pinpointed here. If we pinpoint the position of the electron, then the energy of the electron is uncertain. Energy is uncertain. And so we don't know what that electron's energy is. Because how do we pinpoint electrons? Usually the way we pinpoint electrons is by shining photons on them. And when we're thinking about energy, the energy of an electron is going to be related to its velocity. Its velocity is the direction and speed it's traveling. And so let's say originally the electron was traveling like this, along this trajectory, but when the photon hits that electron, since electrons aren't very massive, h mu is just the symbol for a photon. When a photon hits an electron, the electron's path gets changed. And therefore, its energy gets changed. And so trying to observe it is just not possible. And so if we pinpoint the position, then the energy is uncertain. But if we pinpoint the energy, let's say the energy of the electron is minus 2.179 times 10 to the minus 18 joules, then what do we know about its position? Well, if we pinpoint the energy, that is, we minimize the uncertainty in the energy, then the uncertainty in the position goes up. So pinpointing position means we minimize the uncertainty in the position, but the energy uncertainty goes up. We pinpoint the energy, that is, we minimize the uncertainty in the energy, which I'll call delta E or delta P. Then its position's uncertainty grows. And so if we know the energy of the electron, then we don't exactly know where it is, but we're not totally blind here, because what we have is we describe the position in terms of probability. And so we could use the bird analogy for this. The bird analogy is like this. Let's say there's a nest here. And we know the bird has, let's say it's just its standard energy. Its standard energy, that means the bird can travel a certain distance away from the nest. And so most likely, if it's just on a regular diet, maybe, it stays close to the nest, but sometimes it'll be farther away. But as we get farther and farther away from the nest at this energy, the probability goes way down of finding that bird, because if that bird has a limited amount of energy, it's very unlikely it's going to be too far away, right? And so the probability of finding it out here is very low. And so this is what we mean by pinpointing the energy. We know the energy of the bird, we just don't know exactly where that bird is going to be. Like 2 days from now, can you predict where its precise location will be? No. Whereas, let's say we pinpoint a bird, let's say we found a bird here, but do we know, is that a high energy bird that just so happened to be close to the nest, or a low energy bird? What is the energy? Okay. Because the higher the energy of the bird, the further out it can venture to find food, right? And so a higher energy bird is going to have a different distribution. These dots are just, at one time we find the bird there. And so what we call this is, a electron density map, or just electron cloud. This is electron cloud. An electron cloud just kind of tells us for this energy of electron, this is kind of where we expect to find it. But exactly where? Oh, don't know. Electron density or cloud. What would you rather know? Would you rather know the exact position of the bird? Or would you rather know the energy of that bird? Because if you know the exact position of the bird, let's say the bird's here, you don't know much else about that bird. You know exactly where that bird's from. And so for us, we would rather know the energy. Because if we see an electron here, we don't know. What is it? Is that a high energy electron or a low energy electron? Who knows? Because a low energy electron could be here, and a high energy might be here too. It's just the high energy could be further out. There's greater probability that the higher energy bird could be further out. It's the same thing, greater probability, but there's still probability it could be close by too. And so those are the probabilities we use to describe the electron. And so we put these two together and then add them to the physics of the electron here. So we go from a one-dimensional box to a three-dimensional box. This would be a three-dimensional box here. So we just take this idea of quantized energy, we have the wave-particle duality, and the Heisenberg uncertainty principle, and we do the physics for this. We come up with the Schrödinger equation. Schrödinger equation. The Schrödinger equation is going to take into account all of this. This is a Schrödinger equation here. In a more simplified form, the Schrödinger equation looks like this. H is taking into account all these, this H with a hat on it, times psi is equal to E psi. This is where E is the energy. And the answers to the Schrödinger equation, psi, these are called wave functions. Both these sides are the same. They're called wave functions or orbitals. And so we get the answer to the Schrödinger equation. These are the allowed states for the electron. How many allowed states are there? There are a lot. In fact, they're an infinite number in an atom. Just like the Bohr model, an infinite number. Well, if an infinite number, we need some quick, easy way of figuring this out. And so we represent that. There are multiple answers. Multiple answers.
What's H hat?
H hat is all this stuff. You see this psi here? Factor out the psi and the rest is H hat. H hat is a symbol that you use to do that. And so this would be H hat psi is equal to E psi.
It's just an operator.
Yeah, it's a Hamiltonian operator, which is energy. Actually, not just multiple, an infinite number of answers, and there are also an infinite number of forbidden or solutions that don't work. And so, an example, for the energy, we could solve the energy for a specific level, but, or we could solve it as an equation. We solve for an equation that's more powerful because then we get all the allowed energies. And so for the H atom, we solve the Schrodinger equation, and we get the allowed energies. And we can list the allowed energies, but when you look at the pattern of allowed energies, it's very easy. The energy just depends on one variable, n, and it's just equal to minus r sub h over n squared, for the H atom. This is where n is equal to 1, 2, dot, 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 all the way to infinity. And so this is good because the theory should explain both the hydrogen atom and the helium and any other atom. And so we get the exact same energy equation that we got from Bohr, exact same, which it has to be because this is based on fact. This is for H atom. For other one electron species, the energy looks like this. Is E sub n is just equal to minus z, which is the atomic number, times r sub h over n squared. And that works too. But what about more complicated atoms? For more complicated atoms, this is the H atom, this is one electron species. For multi-electron species, the energy is a little different. When you solve the Schrodinger equation for multi-electron species, the energy depends on n and one more variable, which is called L. And so it depends on two things, whereas in the Bohr model, it only depended on one. And so this is why the energies for the helium, etc., didn't work with the Bohr model. So L, we'll talk about L a little later. And so we come up with an equation that has N and L in it, and then we can calculate all the energies that are allowed. Okay. And then what about the size? The size are pretty much going to describe the electron completely. So this is just describes the electron. Well, what do we need to describe? We've got the energy, and so what else do we need? Well, we need an idea of its electron cloud, right? The probability of finding that electron. There are two components to this side, but NLM. Psi is going to depend on 3, and so what we do is we don't solve this to a specific answer. We solve this to an equation, and this equation we can use to generate the answers. This is where n is called the principal quantum number. L is called the angular momentum quantum number. And M is called the magnetic quantum number. What do these tell us? Well, essentially the principal quantum number tells us the energy level. The higher the n, the greater the energy. The angular momentum quantum number is also called the azimuthal quantum number. This tells us the energy, but it's not as significant. N impacts the energy the most. And so this primarily tells us the shape of the electron cloud, the probability distribution. And so the shape and energy. But energy, is a secondary effect, not as primary. Primary will be the principal. The magnetic quantum number tells us the number and orientation. We'll talk about that. And so there are infinite number of answers to the Schrodinger equation, and we can figure them all out, without too much difficulty by looking at the equations. Magnetic, number and orientation. Number of orbitals. I'm going to talk about this in just a second. And so let's look at the H atom right now. The energy we can get. And so n equals 1, the energy is just equal to minus r sub h over 1 squared, or minus r sub h. All right, so we got the energy. Now the allowed state will be psi. Okay, now we have n. And so n equals 1. Well, how can we figure it out, the rest? Well, the rest, there are algebraic restrictions on these. And if these algebraic restrictions aren't met, then it fails to solve the Schrodinger equation. And the first one is n. There are only specific values of n that work in solving the Schrodinger equation. And so n equals 1, 2, 3, dot, 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 all the way to n equals infinity. Those are allowed. Everything else is forbidden. That it would fail in the Schrodinger equation. L can be all values from 0, 1, 2, dot, 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 all the way to a max of n minus 1. And so it depends. If n is equal to 3, then L equals 0 and 1 and 2. 2 would be the max because n is equal to 3. And then m has all values from minus L to minus L plus 1, dot, 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 through 0, dot, 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 through L minus 1 to L. And so if L is equal to 0, then m would have one value, 0. If L equals 1, then m would have 3 values, minus 1, 0, and plus 1, etc. And so in this way, we can generate this. And so if n equals 1, then the L value can be 0 up to a max of n minus 1. Well, that's it. And then m value is going to go from plus 0 to minus 0, or just be 0. And so this is allowed. The 1, 0, 0. We call this a 1, 0, 0. And so we'll do that like this. L, the shape of this, let's talk about that. The L designations. If L equals 0, then we call this an S orbital. L equals 1, we call it a p orbital. If L equals 2, a d orbital. L equals 3 is an f orbital. L equals 4 is what? Well, S stands for not spherical. Actually, S stands for sharp. P stands for principal, D stands for diffuse. These come from spectroscopy, because in the spectrum, they saw the biggest one was P, and the sharp one was S, and the diffuse broad one was D, when they looked at these electrons. Then it goes alphabetical, so F, and then comes G, etc. Because they no longer have spectroscopic origin. So we just call them that. And so this is called the 1s orbital. It's because n is equal to 1, L is equal to 0. We only have one of those because there's only one m value. Okay, after that we go to n equals 2. When we go to n equals 2, then we have L equals 0. That's allowed. If n equals 2, L equals 0, then m must be equal to 0. And so this is what we call psi 2, 0, 0 orbital, or 2s orbital. 2s orbital. We only have one of those because we just have one m value. When L is equal to 1, we have 3 m values. We have m equals minus 1, m equals 0, and m equals plus 1. And so this is what we call a psi 2, 1, minus 1, a psi 2, 1, 0, and a psi 2, 1, 1. And so the m value tells us we have 3 orbitals, right? Because we have 3 different m values with different orientations. And those orientations are often put into a coordinate system. So we might get a 2px, a 2py, and a 2pz, which are orbitals. Then we can go on. N equals 3. see a punch there. But I'm out of time. Am I out of time? Yeah, I'm out of time, so I gotta stop here. We'll continue this next time.